please welcome Peter Stugay. Thank you.
All right. Thanks, everybody. I'm here to talk a bit about hardening hardware and choosing a good BIOS. Let's see what this means. So, yes, what will I say? Introduction, just briefly about me. Hardening hardware. Why should we care about hardening hardware? What's the point? The software seems to be working fine, right? I'm going to look at some well-known hardware attacks and attack surfaces that are quite open on any machine, really any machine today. Let's see if we can do something about these open attack surfaces and look inside a machine. Well, first of all, look at some schematics and then look inside a machine and see if we can make some changes, maybe. Part of this is also choosing a good BIOS. Pun on the name, bad BIOS, of course, but the point, I think the point is important. Firmware is, in many ways, the root of trust in our software stack, because it is this first software that runs on the machine. So we need to be aware of this software, and it's not for me. Need to be aware of also the firmware in our machines, and maybe there's even more software laying around in the machine somewhere that we don't know, that we should also look at. I will, so for the purposes of this talk and the work I've been doing for a while, I consider core boot to be the good BIOS. But core boot is, it's not focused on, I'll get to that in a bit, it's not focused on a single platform, but it is dominantly for x86 so far. So I'm also going to maybe take a moment to talk about non-x86 machines as well, because I think that they will be more important in the future. So I'm Peter. I moved to Sweden. I moved from Sweden to Germany a few years ago. I'm interested, and I've been working with software and hardware and security for a long time. Electronics since I was a little kid. That was always a lot of fun to take things apart and eventually put them back together again. And I care a lot about open source, and I've done for a long time. I think this is really the way to go. I guess you all agree. I work on core boot and libUSB, libSSH2, flash ROM, Osmocom projects, and so hardening hardware. Why? What's this? What's the problem? So the problem is that security is not really a market value. Nobody is buying millions of computers because they are secure. Instead, it's things like cost, or size, or battery lifetime, or screen resolution, or screen size, or the number of gigahertz, or the number of megabytes, or terabytes, or exabytes, the color of the cherry key switches, or maybe the Windows version, and the last one, I admit, I did make up the length of the included HDMI cable, but I'm sure that some people will buy a machine based on that as well. So yeah, security is not on the list, and sure, yes, there are a few buyers that buy machines because they are secure, but they don't matter. There are too few. Someone might argue that, well, okay, I buy a device or a system that just works. It just works. Then it has to be secure also, right? Because it is really working. It's only doing what I want it to do. Well, actually, the systems that function that way, that tend to just work, they are usually so simplified, so simple, so restricted that, yes, they will do the thing reliably that they've been designed to do, but they may be doing other things as well, because the only way to ensure that these systems really do only what they were designed to do is to lock them down, and to lock them down hard so that you and I can't do anything with them. besides point at colorful pictures and icons. So how does it just work? How does it work inside? That's what this talk is about. Isn't the hardware hard enough? If we're buying hardware, it's a machine, right? It's something physical, something tangible. We can touch it. It is what it is when we buy it. But really, it seems to be the tendency that hardware changes quite a lot under its lifetime. Hardware is becoming softer, in fact. There are firmware updates everywhere for every single device. USB 3.0 controllers, hubs. I believe that the USB 3 or the XHCI standard was finished so quickly that devices were put on the market before they were actually even compliant, and the compliance was made after by designing in reprogrammable parts of these controllers with external memory. So it's not that it was hidden or anything. It's just that these devices had to be finished and shipped so quickly that they couldn't be, or they had to be shipped so quickly that they couldn't really be finished before they shipped even. So hardware isn't that hard. Hardware is pretty soft. Feature phones. I have a cell phone. Some people don't because they don't like cell phones. I think that's agreeable. I do have a cell phone. I got a new cell phone about a year ago or so. I walked into a random store and I bought the simplest possible cell phone that I could buy for the least amount of money in a new phone. So it was a candy bar phone because I like that format. I call it a dumb phone because it isn't a smartphone, but it still has firmware updates. Raise of hands, how many people have had a device ask you to download and or install a firmware in the last 6 months? That's almost everybody. All right. At the moment, we have CPU microcode. We've had that even for almost a decade. Updates to the actual physical processor included in the PC firmware. As far as we know, introduced, 2004 is the earliest press I saw about this for the Pentium Pro. You remember those? That's been there for a while now, and the immediate future, I'm pretty sure, is going to be reconfigurable processors if they're not already in use on the market. I did a fun project not so long ago, actually just last night, with the BeagleBone, which has a nice co-processor that runs independently of the main processor, and you can now load a new firmware to it, and it does other magic things. Right. So this already exists in some special cases, but I'm quite sure that we're going to see reconfigurable computing explode in 10 years, have exploded already in 10 years. So devices aren't just hardware. There aren't really only these physical, tangible things that we go into a store and buy. I mean, we do that, but they come with a thick stack of software. They come with a huge amount of software. And knowing our tools is really important if we want to do the best we can with these devices, with our computers. So my comparison here is with carpenters. If you have a skilled carpenter with brilliant tools, then they can make fantastically beautiful carvings and furniture and so on. And it's the same thing with software developers. I know many software developers are quite uncomfortable with going into hardware and looking at hardware and messing with hardware and destroying hardware. But actually, that's a lot of fun too. Just don't inhale the smoke. It's not so good for you. But start with simple things and destroy them a few times, and then make things. It's good. The current state is sadly that we really don't know that much about our hardware, the PCs that we are using today. We used to know PCs quite well when they were new, but that was 30 years ago, and we haven't really been paying attention along the way. Meanwhile, it's just a few companies that have all the knowledge and know-how, and I don't think that's so good. Sad face. So know thy hardware. How can we do that when we don't even own the machines? I was saying that the devices that just work, so the ones that get popular, the ones that sell, they are locked down. The iOS is a good example, Windows RT is another good example. Android, well, there are some Android devices that are more locked down than others, but there are a few systems that are really both end-user devices and open for modification. You have to choose either or at the moment. Desktops, laptops, server PCs, they're all Microsoft Windows machines. If you're talking to a hardware manufacturer that manufactures laptops, let's say, they don't think in terms of, well, this is a hardware, this is a machine that can run any operating system. It can run DOS, it can run Windows, but it can also run FreeBSD and it can run Linux. They think of this as, this is a Microsoft Windows machine. That's the purpose of this product. It's going to run Microsoft Windows. Anything else is an accident. That's really true. It's sad, but it is. That's the case. ARM tablets are Microsoft Windows RT machines. All the Macs are obviously Apple OS X machines. And a lot of people like OS X machines and like OS X, but, well, it's manufactured, it's designed, it's produced to be only this one thing, and it's not meant that anyone looks into it, goes inside of it, makes changes. Cell phones. Again, Apple iOS machines, they made an incredible accomplishment entering that market, or Google Android machines. And the Android cell phones, I'm hopeful there that we can actually be making some good open-based, open source systems using those machines. Of course, how deep does the rabbit hole go? So there's microcode in the processor, as I mentioned. Microcode, the way I see it, the microcode that ships inside of the processor is hardware. It's part of the hardware. It defines how this processor executes instructions. So microcode updates are hardware as well, the way I see it. Either you trust the microcode that is in there, and if you do, then you might as well trust the microcode updates, or you don't trust the microcode that is in there, and then you can't really use that CPU. Then you have to, well, I don't know, make your own, perhaps. There are, by the way, a few good presentations on exactly that topic, which I recommend that you all go see, and maybe you will like making your own CPUs. Please do. There are some idealists that who sometimes insist on removing these microcode updates. So in core boot, we get interest from lots of people who think freedom is important and who want open systems as well. And they say, okay, I really want to build a core boot that does not apply any microcode updates. I want to run only exactly what shipped from the manufacturer inside the physical device, even though the microcode updates fix bugs, presumably. And, well, not only presumably, they actually do fix bugs in some cases at least. There are erratas together, delivered together with them, or available for the microcode updates, which describe what is this microcode update used for, or what does it do. Sometimes the processor doesn't work reliably without the microcode update. What do you do then? Do you apply the microcode update or don't you? Sometimes it doesn't even start properly. Quoting one of these users, or one of these users, it's the principle of saying, I'm removing part of your control over me, so me being the user of this processor and your control being the control by the manufacturer. But what degree of control do we want? So if we want to control our user land, then there's GNU and other open source operating systems, BSD is a good one. Kernel, Linux, BSD. Firmware, there's coreboot on x86 and coreboot on ARM and other bootloaders on other platforms. What about microcode? What about hardware? Doesn't look so good there at the moment. But my software is running just fine on this machine. I can take this machine and I can install my whatever and run it and it works fine. Or does it? Do you really know? Yes, it looks like it's working fine, but is it somehow leaking information about your data in a side channel on a network interface that you don't know how it works? Do you even have equipment to find out if your software is actually running fine and doing what you want, and if the entire system is doing what you want and nothing more? Really, it's not so easy. So there are lots of attacks on laptops, for example, or that are lots of attacks that are practical for laptops. There's an old, well-documented FireWire exploit, or IEEE 1394, which is basically a remote memory access bus. It's really fast. It was designed for hard drives, external hard drives, and they have to be, they need a fast interface. So yes, of course, IEEE 1394 has to be fast. So let's do direct memory access from the outside. Except if you don't restrict where the memory accesses go, then, well, you can access any memory. That's not so good. There's advanced management technology, which is built into every single Intel chipset after, well, 2005 or 2006 or so. Every single chipset has this. If you buy, so there's a cutoff point that I've noticed in experimenting between the 945 chipset and the 965 chipset. So we're talking 2006 generation hardware. If you power on the 945 chipset without any firmware in the boot flash, then nothing happens. It doesn't work. If you power on the 965 chipset without any contents in the boot flash, there's an IPv6 packet coming out of the Ethernet port. That was 2006. So check out Patrick's talk, Patrick Stevin. He's doing a talk, I think it is tomorrow or maybe the day after tomorrow, about his work on advanced management technology. It's really interesting. It's a serious attack vector, so someone on your network can access whatever your network interface can access. PS3, so there was a USB fuzzing attack against the PlayStation 3. The guys talked about that a few years ago here and other places. We know about BIOS bootkits. You get some kind of bad software into your system. It rewrites the flash memory, the boot flash, and stores some kind of persistent version of itself there. So it stays in your system once it's gotten in. We can summarize this by saying that systems can be influenced simply by injecting data in many different ways on many different standardized interfaces, and we get results from just application denial of service, where things don't work, they crash or whatever, to actual kernel code execution, or even worse, direct memory access. So that's stage one. That's something someone can do if they pass by your computer for a few seconds. They can connect something and they can read your memory in the machine. Several different ways to do this already demonstrated. Some of them have had protections published and implemented, and that's good. But it's still a big risk, I think. And not all of them have been looked at in great detail, and it's not so easy to look at them in great detail because these are closed systems. They aren't meant to be looked into, actually. So commodity machines, commodity systems, they have lots of attack surfaces. There are several DMA interfaces exposed to to the outside world, offering up private key material and whatever you have, whatever else you have inside the machine. The FireWire, the IEEE 3094, if you have a laptop, maybe you have a card bus slot, if you have an old laptop like I do, or maybe you have an express card slot, which is PCI Express, so even faster access to your private keys. PCI Express, on this machine I can't do it that easily, but I have a small netbook also where I take off 2 screws and the entire backside comes off. It's convenient because I can replace the wireless networking card. It's also convenient for an attacker who wants to replace my wireless networking card. The wireless networking card, which by the way is a radio interface which is connected to the PCI bus. So this is a radio transmitter and receiver which is connected to your memory bus, my memory bus. Well, not the memory bus, but it can access the memory on its own. All PCI devices, all PCI Express devices, they can be bus masters. They can say to the chipset that, hey, I want to read from memory now. And they get the memory contents. It's really easy for them. And okay, so yeah, this radio, this wireless networking card, it only implements the standardized wireless networking protocols, right? Well, do you know? I don't. I saw, I saw something about, oh right, yes, no, I forgot his name again. Vasilis, a guy I met in Berlin in May this year. He wrote a master's thesis on this advanced management technology also several years ago, so on older versions of that hardware. And he found that actually sometimes that's enabled over wireless network as well. So the wireless networking card will connect to an access point all on its own, and this is the card that is connected to your memory bus. Docking station connector, Ethernet. The Ethernet needs to be fast as well, so it's also on the PCI Express bus, right? And the docking station as well has lots of expansion capabilities and has fast peripherals, so also direct memory access. LPC is low pin count, 4 pins used to replace the ISA bus that nobody wants to have anymore, used for slower devices, but it's also available on the docking station of this machine. So what other? So these are the serious problems. These are the problems that allow someone to connect and just read memory, like that, right away. So we need to do something about those if we want to have a chance at hardening this machine that we have. There are, of course, other ways to get data into the system and try to mess with the software that is interpreting the data that you send. You can try the hard disk interface. I saw at OHM this year, someone implementing their own firmware in a hard drive controller, replacing data getting sent back to the host system. So you can do that, apparently, easily enough. USB is a good way to send data into any system. Well, except, so since I've done a bit of work with USB, I also know that the USB, the way the USB specification is built, it's quite a thick, already a thick specification, and that, well, that might be worrying, but it's narrow, so it's fairly easy to actually read all the code and read the entire specification and understand how this should work and see that the code, check that the code doesn't do anything else. And kernel USB code doesn't have to deal with the data. The data goes directly to user space if it's a user space driver that is talking to the USB hardware. Or, of course, it goes into the kernel driver if it's a kernel driver talking to the USB hardware. All graphics ports, VGA, DVI, HDMI, they have a back channel for the display ID. So the display can say, like we had with the Beamer here, I support these resolutions. Which one do you want to use? Pick one. This is an I2C bus, usually, and if you have a Linux system with a kernel mode setting driver, the kernel mode setting driver, the driver runs in the kernel, reads this data and interprets a data structure. So is that perhaps an attack vector as well? 2 pins on the VGA connector and the microphone. So if the microphone can pick up ultrasonic frequencies, then you can send, of course, inaudible commands to the computer or whatever, I don't know, to the processor that runs microcode that you don't know, that we don't know, that I don't know what it does really. Maybe it responds to this ultrasonic sound stream that is being played by a speaker in the next room. What can we do to get rid of some of the worst problems, at least? We can disable the DMA interfaces. We can try to disable the DMA interfaces. We need to try to disable the DMA interfaces if we want this machine to be a little bit more resilient. The Wi-Fi needs to go, we can't have a radio transmitter with direct memory access, just no way. And ideally the Ethernet as well, unless you always connect to trusted networks, like here at the Congress. Firewire, somehow disable card bus as well would be good. Step 2, look at source code for problems with just malformed data. You would think that programmers would know how to actually interpret data by now, but it seems that we don't yet. And maybe we'll never will. I hope that we will, but who knows. So we have to look at the source code and check that actually the data that we do allow into the system, it doesn't have very many problems. It doesn't have any problems that we can find, ideally. It doesn't have any at all. Step 3, choose a goodBIOS. And step 4, write protect the boot flash. So in doing that, we would have a machine that is resilient to bootkits because the flash can't be reprogrammed. We have taken out the microcode if we're worried about that. We've audited all the source code that is running on firmware level, on kernel level, because we all read the kernel every day, right? And user space. The X server is a good read. And disable the DMA interfaces. So I tried to do this. No, I didn't try to read all of the kernel, and I didn't try to read all of the X server, but I tried to read some code, and I tried to choose a goodBIOS, and I tried to disable the DMA interfaces. So step 3, they're choosing a goodBIOS. I went with core boot. There aren't very many options, and I know core boot, so the choice was easy. Core boot runs well on, I'll get back to that, on many systems, but in this case I chose one particular system, a ThinkPad, where it runs well enough. I don't know if you recognize this quote. It's commonly used by Dave Jones of eevblog.com. It's a good, he's a fun guy. So don't turn it on, take it apart. Let's see. So this is, let's start with the description of the machine. If you look around the internet, you can find schematics of all sorts on all kinds of sites. And this is the first page, the overview, the block diagram of this laptop. I've zoomed in to the interesting parts. The most interesting part. So the ICH7, that's the chipset, and I don't know if it is readable. Yeah, it's pretty readable. It has a bunch of interfaces listed there, the LAN, the Ultra, the parallel ATA, the serial ATA, the LPC that we mentioned, the PCI Express. And these connect, so at the top we have this RICO chip, which is driving, as we see, to the left, IEEE, and to the right, PCM CIA slot and card bus. It says PCMCIA in the schematic, but it's card bus. PCMCIA wouldn't have been quite as bad because it's a 16 bus without, as far as I've seen, without direct memory access, but card bus is quite a bit more because card bus is a proper PCI bus, just hot pluggable. And the RICO chip is just a PCI to PCI bridge. So that's problematic. We need to do something about that. We see that the mini PCI Express W1 card, wide WAN card, the 3G, is underneath it. That's connected over USB. And in order to have any kind of connectivity, and because I know USB well and I've looked at a lot of the USB code, I decided that, well, I think USB is okay. I'm going to allow USB still there. Otherwise, there's really no way I can get anything in or out of the machine, as it turns out. The Wi-Fi card, that has to go. The built-in Ethernet is also on PCI Express. So someone could walk by and send a magic packet, or I don't know, talk to the advanced management engine somehow, or the management engine over Ethernet and do things to my machine if I leave it around. I don't like that. Looking a little bit further down, there is a keyboard controller, and Ralph Philipp Weinmann, he talked about that particular controller a few years ago, and that was also one of the inspirations for this talk. This keyboard controller can of course record all your keystrokes, and it can send them out in many different ways. This is on the LPC bus, the keyboard controller. It does many other tasks, as it turns out, and is worth looking closer at. But being on, so even though it is on LPC, it doesn't have the capability to do DMA. It's not DMA. It cannot initiate DMA requests. So that's not so bad. The Super I/O has, on the other end, serial ports and parallel ports, which are also not so easy to use against the machine, to use against the system. There's the boot flash. There's a debug connector that isn't exposed. It's inside of the machine. There's a TPM chip, and over on the far end, there's the PMH. That's another second embedded controller that does power management things, and actually that one proves to be quite helpful. So that's the LPC bus. Oh, right, and the Super I/O. Oh, right, the Super I/O in the middle. That's I confused it with the Super I/O on the bottom. The Super I/O in the middle is actually something we need to look quite closely at, because it puts the LPC bus all the way down to the bottom of the screen. This thick line that you see there is the docking station interface. So the thick line, whatever is on the south of on the thicker line, is inside the docking station. So there's an LPC bus going out to the docking station as well. So let's see. Let's start with the VGA. That was outside the previous image. The interesting thing here is the signals on the far right, the DDC clock and data. That's the I2C interface that is connected directly to the port and goes into the chipset, into the kernel driver, just on 2 pins on the outside of the machine. So how can we get rid of those? Well, the easiest way seems to be to remove these 2 inductances, the L21 and L24. And indeed, that works just fine. I didn't actually try using an external monitor after having done that modification. It might not work, or it might work if one does the X-Rander trick that we did, that I got some help from the Video Angel with just before the talk here. Next thing up is the FireWire SD card and card bus controller. Unfortunately, that's all in one chip, so we have to get rid of all 3 of them at once. It turns out, looking closely at, so the block on the left is that controller chip. On the top, top right, there's a card bus PD. So card bus power down, that sounds good. Signal that goes into a ball that is called hardware suspend for this chip. That sounds good. Looking on another page, this card bus power down, it's the second from the top on this page. It's connected to R461. So a pull-up resistor holding it normally active so that normally the card bus is working. But well, maybe we can remove that resistor and connect it to ground and to that way permanently shut down the card bus. This is the Ethernet chip. It has as well a disable signal, third from the top, device off, it's called, a GBE disable. So we could also remove the resistor there and connect that to ground, tie it to ground to permanently disable the flash chip, the Ethernet chip. All right, that's all of those. And how does this look then? Let's see. Oh, I should have taken out some. Didn't I do that? Oh well. Take out all the screws from the bottom, and on the top, lift the keyboard up. Keyboard comes out. Disconnect the keyboard. Looks like this now. Now bend the front a little bit. There we go. The top comes off. Scalpel time. So we found this, this Super I/O chip, the LPC bridge. It's neatly situated right next to the battery, so in the middle of the board. Just make a bit of room and cut off the plastic tape above it. There we go. Here's a pinout from the datasheet, which is very easy to get, thankfully. All the pins that are labeled D in the beginning, they go to the docking station. This chip is really a docking station chip. It's made to do nothing else. All the ones with the D, they go to the docking station. So we want to cut those at the pin, at the chip. Cut those pins at the chip. Here we go. Careful. I hope it's possible to see, but the pin on the corner there is anyway gone. And yeah, we do it a few more times. All the pins with the D. And a few more pins, and in the end we get this. So by cutting the pins, they don't, of course, come off the PCB. So I have to take them, clean them off after cutting them from the chip, so that they don't short in any way, and clean up the PCB a little bit. And in the end, we have that for the docking station. So that's not so bad. I managed to destroy one laptop so far, but it's only one. If you have a good scalpel and a steady hand and a good eye or a magnifying glass, that's very doable. All right, put the tape back on. So this is a fully equipped ThinkPad. It has the wireless and the 3G on the bottom right, and a modem. Let's start with the speaker. You can't trust those. And, well, you know, I mean, I don't know, right? A modem, who needs that anyway? Take out some more screws and take out the Wi-Fi and the 3G card. Then we need to take off a display cable. Get the antenna wires loose and the power cabling as well. Which is a little bit tricky because this is a compact machine, so have to be careful, but it works out well. The modem connector we don't care so much about. Unscrew some more screws. take off some tape for the wireless antenna. And finally, we've gotten, oh right, the hard drive adapter board as well needs to come out. Finally, the main board is free. Well, for some value of free, we can take it out of the machine anyway. Front side, back side. There's a microphone. We'll get to that in a second. Also underneath after much searching, underneath the wireless cards, this R461 was found. So take off this sheet of protective tape. And it's the top one of the 3 resistors. That's R461. It's not labeled on this board, unfortunately, but it was on another board. So take that off, clean up a bit, solder a wire into place. The capacitor right next to it happens to have ground nearby, so that's convenient. Put the tape back and turn the board over. So that's already card bus and firewire disabled. Pry off this protective plastic, which you have to be careful if you do, because it tends to rip easily. Right, microphone is soldered into place between the USB and, well, slightly above the USB and the firewire socket. Put the mainboard up on something and, well, heat the soldering joints until the microphone comes out. It actually falls out on its own as long as you encourage it a bit. Boot flash. So the boot flash we want to reprogram with our goodBIOS. For example, with another ThinkPad, and a handy clip, and the flash ROM software. So this machine had a Macronix flash chip. In these ThinkPads, there are 2 different ones, the Macronix and the SST that I've seen. The Macronix one and WinBond as well, they have a neat feature where a write protect bit can actually be set non-volatile. So you have to set it only once, and it stays set, whereas the SST chip resets this bit every time you boot. That's not so handy. So because this was a Macronix chip, I also solder pins 3 and 4 together. Maybe it's possible to see on this, on the flash chip, the 2 rightmost pins on the side that we can see are bridged together. The 3rd one is the write protect pin, and the 4th one is ground. So connecting these 2 together and having set the write protect bit actually ensures that the boot flash will not be writable anymore. You have to unsolder this bridge in order to reset or to clear the write protect bit in software. And SR in this case is the status register. The 0x80 means that my slightly patched version of flash ROM, which always sets this write protect bit in the flash chip, ran successfully. When putting the mainboard back together, be careful with this wireless switch if you still want to use some kind of wireless, because the plastic thing that moves around is kind of sensitive. It's easy to break the switch off the mainboard. Put the casing back together. Put the keyboard in. Put some screws in and power up, and hopefully you see an open source firmware running on the machine. Yeah, right. No. No, not just yet. I'm not done just yet. Yeah, 1 minute more. All right. Yeah. Where is it? There we go. Oh, too far. All right, here we go. So I wanted to talk a bit about this as well, the BIOS economy. I guess we're out of time for that. The BIOS vendors, they have an excellent setup where they sell their product to the ODM that creates the hardware design, and then the OEM, so that's Dell and Lenovo and whoever, they have to pay license fees to the BIOS vendor if they want to use the implementation of the BIOS that the ODM already implemented. So, given this BIOS economy, there are two choices for us. Buy a system which sends money to the BIOS vendor, or buy a system which doesn't send money to the BIOS vendor. Enter coreboot, open source BIOS replacement. Started in 1999. A few mainboards work really well. Can we buy it today? There's one popular vendor, Google, that sells machines with coreboot on them to consumers, and that's the Chromebook. Mostly open firmware, because on Intel machines, on Intel systems, it's actually impossible to have a completely open firmware at the moment. AMD is much better. But there aren't any Chromebooks with AMD processors. Locked to cloud services, one might say, well, once you bought the hardware, you can use it any way you want. Freescale and Allwinner ARMs look really good. Oops. So, security, taking a bit of a jump, security starts far, far, far below the crypto, and please make open firmware a priority, even if it is really inconvenient to repurpose a Chromebook. Thanks to the Engels, thanks to the coreboot community, Stefan, Patrick, Sven, and all of the guys. Thanks to Ralph Philipp Weinmann, who made the talk The Hidden Nemesis. And thanks to you for becoming more aware of what your hardware is doing.